Hello there. In this lesson, we're going to use the mole concept to determine the percentage composition of compounds, as well as empirical formulas. And this is something that's sometimes done as a lab activity. A good example is when you react a piece of magnesium under a lot of heat. It'll react with oxygen and you'll end up with a nice powder of magnesium oxide. And you can work out from the mass values that you measure what the formula of that compound will be. So let's have a look at how we do that. So first of all, you need a basic idea of how mass is related to the different components inside of a compound. So use a nice simple example here with water, and you know that the number of particles is the ratio in the formula. So you get 2 hydrogens for every 1 oxygen in water. So using our mole concept now, since we know that particles are related to mass through the molar mass values off the periodic table, we can work out what the percentage of the mass would be for each of those elements as well. So instead of 2 to 1, which is the particle ratio, we can work out a mass ratio as well. So to do it for hydrogen, we know that 2 grams, 2 moles of hydrogen for every 1 mole of the whole thing of the water will be the percentage of hydrogen. So we can take our 2 grams, which is the hydrogen, and then we will divide that by the 18 grams per mole. And this is 18 grams per mole of water. And to make this a percentage, we'll multiply by 100. And let's see what we get for that. On 2 divided by 18 equals, oh, look at that, 11%. 11% hydrogen. And then for the oxygen, we can do the same thing. 16 grams per mole is the mass of oxygen in a mole of water. And then, of course, the total mass is 18 grams per mole. That's oxygen, that's water, times 100. Should give us the remainder, which would be 89% oxygen. So you can do that for any elements in any compound. Just take the molar mass of the element that you're looking at over top of the molar mass of the total compound, and you got yourself a percentage. Alrighty, let's give this a try. First off, you're going to want to look up the molar masses of the elements that are part of your compound here. Calcium turns out to be 40 grams per mole, and fluorine is 19 grams per mole, which means the total for this guy is going to be 40 plus 19 plus 19, which is 78 grams per mole. No, I don't need that. Okay, so then if you want the percentage of calcium, you take the 40 grams per mole, that's the calcium, and you divide by the 78 grams per mole, which is the whole compound. And multiply that by 100, and that should give us, let's see here, 40 divided by 78, and, oh, something on my calculator from before, 40 divided by 78 is, there it is, 51.2, I guess we'll just say 51%, 51% calcium, which means you don't even have to worry about the fluorine one. You can just do the difference. So 100 minus 51 equals 49% fluorine. There we go. Okay, so we got one that's a little more complex here. We got lead, which is 207 grams per mole, just roughly. Oxygen's roughly 16, and hydrogen's roughly 1. So the total molar mass of this whole compound, since we got 2 oxygens and 2 hydrogens, this would be 32 for the 2 oxygens and 2 for the 2 hydrogens, and so the total there is 207 plus 34 is, yay, 241 grams per mole. Okay, so then we can take, for the lead, it is going to be the 207 grams per mole all over the 241 grams per mole, and times 100 equals, so 207 divided by 241 equals, we've got 86%-ish lead. And then for the oxygen, it's 32 grams per mole go to the 241 grams per mole times 100 equals, so 32 divided by the 241. This time it's 13%-ish. And so that takes us up to 99%, and that means that the hydrogen is going to be, the difference, minus 86 minus 13 equals 1% hydrogen, roughly. Okay, so hopefully you got the basic idea of how to work out percentages of the mass using the molar masses. Okay, so using that idea of percentage mass and knowing that the mass quantities are related to the formulas and the particle quantities that you have, the next step is to be able to come up with a formula. And the first type of formula we're going to look at is what's called an empirical formula. Empirical formula means that it's the lowest whole number ratio of the elements in a compound. So I got a couple here that aren't empirical formulas. This one here, obviously both have 2's, and so it means we can reduce that, make it smaller, smaller ratio, and NaCl would be your empirical formula. And so all ionic compounds are going to be empirical formulas. They're always going to be the lowest whole number ratio of elements. Now, this one you're probably familiar with. This is good old glucose. And you can see that it is not an empirical formula. So molecules don't have to be in an empirical formula state. We can definitely still reduce this down to 1 carbon, 2 hydrogens, and 1 oxygen. And so empirical formula for glucose is much simpler than the actual formula, the molecular formula. All right, so when you're going to find an empirical formula, there are nice 3 easy steps to follow. First off, you want to find the mass of all the elements that are part of the compound. And then you want to convert the mass of those elements into moles of elements. And you won't necessarily get whole numbers there. And then you need to divide in order to end up with whole number ratios so that you finally end up with the lowest whole number ratio. And that will be your empirical formula. So let's follow those steps and see if we can work out some empirical formulas. So here we go. We got a substance, a compound that is 50% sulfur and 50% oxygen by the mass. So whenever you have these percentages, because they're going to be the same regardless of the quantity you have, it's easy to get yourself to the mass values by assuming that you have 100 grams, because these percentages are per 100. So that means instead of 50% sulfur, if we're assuming we have 100 grams, well, that's going to be 50 grams of sulfur. And the same thing with the oxygen. So there we go. Step number 1, we have our masses. Now what we want to do is convert this into moles. So we're going to use the molar mass of sulfur, which turns out to be 32 grams for every mole of sulfur. And we're going to do the same thing with oxygen. It is 16 grams for every mole of oxygen. And we'll work out the number of moles of each of these proportions or masses. So 50 divided by 32 is 1.56 moles. And same thing here, 50 divided by 16 is 3.125 moles. You can keep lots of digits here. We're not worried about the quantities until the end, which we're going to round off to nice whole number ratios. So this is moles of sulfur, this is moles of oxygen. The last stage is to get to the lowest whole number ratio. So we've worked out mass here, and we worked out moles here. And so the lowest whole part comes by dividing by the smaller value here. So the 1.56 is smaller than the 3.125. So we're going to divide both by the smaller value. And what you get when you do that is this is going to be a 1, and this one's going to be a 2, and therefore your empirical formula is 1 sulfur and 2 oxygens. Ding, ding, ding. There you go. You got yourself a formula. So our first example was very nice because our lowest whole proportions came out to be nice even numbers. But that doesn't always work out to be the case. And what you can do is if you end up with like a decimal in your ratio, you can multiply by some quantity in order to get a whole number ratio. So if it was a ratio of 1 to 1.5, if you multiply everything by 2, 1 times 2 gets you to 2, right? And then 1.5 times 2 gets you to 3. So then you've got yourself whole number ratio rather than having fractions or decimals. If you got something like in the 0.3 range, you can multiply by 3 and you will get 3 to 4 as your ratio. If you get something that's in the quarter range here, you're going to multiply that by 4 and you'll end up with a 4 to 5 ratio. So just have a look at what multiple you could use for the fractional component of the ratio in order to make it a whole number. Usually it won't be much more than 2, 3, or 4. Okay, so let's try one where we're not given the quantity of each element as a percentage. And this is closer to what might happen in a lab activity. You start off with a sample, you measure the mass of the whole thing, and you know it's made of these two elements. And then say you react it or decompose it, and all the oxygen is removed, flies away, part of the atmosphere, and you're only left with the iron that's left over. And we want to determine empirical formula of this compound. So the iron mass is given to you right away, being 35.36 grams, right? And for the oxygen, you're going to have to subtract. We started with 50.51 grams, and we're going to subtract the 35.36. This is iron and oxygen. This is just the iron. And so what you're going to be left with will be just the oxygen. So 50.51 minus 35.36 equals 15.15 grams of oxygen. Awesome. Okay, so that's the mass component. Next part we want to do is find moles. So we're going to multiply by the molar mass, or divide as the case may be. So iron has a molar mass of 55.8-ish, 55.8 grams per mole. And oxygen has a molar mass pretty close to 16 grams per mole. And that'll help us go to moles of iron and moles of oxygen. So let's have a look here. 35.36 divided by 55.8 is 0.633 moles of iron. And then 15.15 divided by 16 is 0.946 moles of oxygen. Should be a 7, I guess. Right, okay, so now we have our moles. Now we want to find lowest whole number ratio. Okay, so if we divide both of these by the smaller one, which is the iron, 0.633, we will end up with a 1 here, and if I'm not mistaken, divided by 0.633 equals, there you go, pretty much 1.5. So since we can't have halves in our formula, we're going to multiply this by 2. That'll give us 3. And whatever we did to the one side, we got to do the other. So that'll give us a 2. And so the ratio here is going to be 2 irons for every 1 oxygen, which means Fe2O3. Ding, ding, ding. Okay, so empirical formulas are great for ionic compounds because they're always empirical. But molecular formulas, not so much. So what you need to do is once you work out your empirical formula, you have to compare it to the molar mass of the actual compound to make sure that they're actually the same. And if they're not, you have to multiply in order to find out what the actual molecular formula will be. So in our example here, if you go through the whole process and you worked out the empirical formula of a compound is CH3. So CH3 isn't really possible. If you try to draw that, you'd have free electrons hanging around, and you won't have a stable molecule. And its empirical molar mass doesn't match the molar mass of the actual compound. So if we work out our empirical molar mass and of CH3 is going to be 12 plus 3 is 15 grams per mole. And the molecular molar mass is 30 grams per mole. So that means that the actual molecule is double the mass of the empirical formula. So what you do is you just figure out what the multiplier is here. Here it's easy to see it's times 2. If it's not easy to see right off the bat, just take the 30, the bigger one, right, the molecular molar mass, divide it by the empirical, and you'll end up with the multiplier. So then what you do is you take your empirical formula, CH3, and you're going to multiply by this multiplier value for the molar masses. And what you do is just change the subscripts by the factor, right? So the invisible 1 there with the carbon becomes a 2, the 3 there with the hydrogen becomes a 6, and that will be your molecular formula. Yeah, kind of squeegee there, I don't know what happened. Okay, great. Talk to you soon.